Cool. Hi, everyone. I'm Audrey. I'm a fifth-year PhD student at UC Berkeley, co-advised by Jan Stojka and Natasha Crooks, working on database systems. And today, I'm super excited to tell you about a new direction research that we've been exploring here at UC Berkeley. So actually, the talk will be two parts, because I think I'm very generous, got a lot of time to tell you guys about a lot of exciting research we're doing. The first part of it is going to be about how we sort of re-looked at the problem of transaction processing, especially with respect to performance, and how we're trying to do faster transaction scheduling. And in doing so, I'm going to tell you about another piece of work in which now you have scheduling, there's also now the problem of what's fair, because in scheduling, you're basically giving priorities to some people, and you're obviously slowing some people down. So then you have to consider, how do we balance getting faster performance, but also making sure we're not starving anyone. So I'll start with fast transaction scheduling. So this is work that actually appeared in VLDB this year. So I gave this talk just a couple of weeks ago in Guangzhou. This was work in collaboration with Meta and a bunch of other folks as well. OK, so quick review. Transactions are sets of operations that appear to take effect atomically, for those you know. And this abstraction has been very successful. It's been adopted by all the database, almost nearly all modern database systems. And to make sure that transactions can execute correctly, the database uses a protocol called concurrency control that's basically mediating the conflicts between concurrent operations. So the goal of concurrency control is to try to get correct results as fast as possible. So usually that means maximizing throughput. And unsurprisingly, there's been tons and tons of research on concurrency control. A quick Google scholarship shows more than 1 million results. So the question is this a closed book? Well, not quite. And the reason for this is because that all these concurrency controls, you probably heard of things like two-phase locking, optimistic concurrency control, multi-versioning. All of these, they're implicitly enforcing some order on the transactions. So the key question, actually, when you're thinking about performance, is what is the schedule that's actually being produced by these concurrency control protocols? So now we've sort of looked. Now the problem performance is actually a scheduling problem. We care about the transaction schedule. So what's the right transaction schedule to be using? Well, we need to go back to the future with Christos Papadimitriou. So actually, a lot of people have looked at this problem in the past. There was papers from the 1970s, and it was found that optimal scheduling for transactions is a very hard problem. And this is easy to see. If you have n transactions, then it's n factorial possible schedules. Unsurprisingly, the optimal schedule is an NP hard problem to go and find, and this was proved a long time ago. And it's for this reason that most modern protocols typically use chronological order. And for the reason, and then they see issues for the same reason that the McFly family in the Back to the Future movie sees issues. So in the movie, Marty's father falls in love with his mother. He gets bullied, and then he continues to get bullied throughout adulthood, and that's why the family's in the sorry state that they're in. For the same reason, most modern protocols, concurrency control protocols, are using FIFO, or first in, first out. They're only dealing with conflicts after they've arrived. So why are we revisiting this problem now, decades after this was shown? Well, the reason is because when the transactional model was originally developed back in the 1900s, it was designed to be interactive. Like people were actually typing in the transactions and then running them. But nowadays, most transactions actually come from programs, right? You write some code, and that actually generates the transactions. So this is an example of a transaction from the small bank benchmark, which is a very common OLTP benchmark. And given this, now there's much more workload information that we can go and leverage to schedule transactions. So how can we actually do better? Now we know that we should be focusing on the schedule. So the main insight that we make is rather than executing in FIFO order and dealing with these conflicts after they've materialized, instead we should try to schedule these transactions more intelligently by proactively minimizing the impact of these conflicts. And specifically, we want to time travel. So the main thing is, though, time travel is pretty hard. Like this is the time travel schedule in the Back to the Future movie. If you screw up, you can maybe cause your siblings to disappear. In our case, you could actually slow down performance. So how do we do this in a way that actually improves performance? Well, we make the key observation that what matters for schedule performance, or what we care about execution time, it changes with what we call the cost of conflicts. And this is how much conflicting operations stall other operations. So to give you a very simple example, I'll show you two transactions in two different schedules. So in this first one, T1 is scheduled first. It's reading X and then writing Y. And then T2 is scheduled next. It's reading Y and then writing Z. And you see here there's this conflict between the write of Y and the read of Y. And assuming you want serializability, then T2 needs to wait for T1 to complete before it can begin operation. So assuming that each operation takes 1 unit of time, the schedule on the left-hand side takes 4 units of time to complete. On the other hand, if we flip the order of the two transactions, so we have T2 run first, it still has that conflict with T1. But in this case, because the read of Y here can run in parallel to the read of X of T1, actually it only takes 2 units of time for the schedule to run. So as you can see, even with a very simple example, very short transactions, still we get like 2x difference in the amount of time it takes to run these two requests. So we capture this intuition with a scheduling policy that basically we want to be reducing these costs of conflicts to lower overall execution time, which we call make span. So our protocol is called shortest make span first, SMF, and it's very simple. So first we start the transaction with the schedule with a random transaction. We find that the starting transaction empirically doesn't matter that much once your workload is big enough. And then out of a sample of the unscheduled transactions, we then iteratively add the one that increases make span the least. And so the runtime complexity is linear with the number of transactions you want to schedule. So I'll give you a quick example of our protocol to build intuition. So here we're going to have a workload of 3 transactions, T1, T2, and T3. So T1 and T3 have the same operations. And we say randomly, T1 is going to start. So our initial starting schedule has these two operations. So there's a make span or overall execution time of 2 time units. Now the SMF is going to consider the next 2 candidate transactions, so T2 and T3. So first, we'll look at what happens if we add T2 to this schedule. In this case, since again we have that conflict between the write of Y and the read of Y, T2 has to wait for all the operations of T1 to complete. So it takes time of 4, so that this particular schedule has a make span of 4. On the other hand, if we have T3 scheduled first instead, you can see that T3 can run partially in parallel with T1 because that read of X can execute concurrently, and then we get a make span of 3. So actually, it's better here in this case to schedule T3 first because it gives us overall a lower make span. And the final schedule we get from SMF is T1, T3, T2, and that's actually optimal for this particular workload. So of course, that was a very simple example, very high-level overview of the protocol. There's a lot more considerations we have in our paper, such as, what about that question of optimality? Can we actually get closer to the optimal, perhaps? So while knowing the optimal is NP hard, we can provide statistical bounds with respect to the entire schedule space. So basically, among all possible schedules out there, we can bound how well our protocol is doing. And there's more details in our paper about how we do that, as well as the overheads. Both performance and storage, how much metadata we need to be storing. And this, we find, has minimal impact, even in production systems. And there's a lot more details in the paper that I would direct you for that, but I don't have time to go over those here. OK, so I've discussed, we have this nice policy, but it works when we actually know all the information. So specifically when we're in an offline setting, when we know both the full read and write set of each transaction, as well as the batch of transactions we want to schedule. However, in the online setting, most real systems, you don't know what operations the transaction are going to access. You don't know how they're going to arrive. So basically, what we need to do here is we need to predict key accesses. So here specifically, we leverage the key observation that hotkeys or high conflict keys have outsized impact on performance. And intuitively, this makes sense because if a lot of conflicts are occurring on these keys and you schedule the transactions that are accessing these keys better, then you're going to get a much bigger win in performance. So basically what we do is we use a simple classifier to go and predict these hotkey accesses. There's also more details in the paper. So our system, our SMF, we implement it in a modified version of RocksDB, and it's pretty straightforward. So our scheduler consists of 2 components, the classifier to predict hotkey accesses, and then the scheduling queues for which the information from the classifier is sent, so we know how to schedule these transactions. We also introduce a new scheduling first concurrency control protocol, MEschedule, that augments METSO. So that gives us more fine-grained control over execution, and that interfaces with the storage layer, which we don't change. OK, so I'll quickly go over some experimental results. So we compare against a number of baselines, including the default OCC implemented by RocksDB. We also compare against a state-of-the-art probabilistic scheduler, METSO, is a standard concurrency control protocol, defer with MBTSO, and finally our system. And we look at a range of different benchmarks, both standard OLTP ones, as well as more ones based more in the real world. And specifically for these results, I'll be focusing on throughput. So as you can see, our SMF has noticeably higher throughput on all the benchmarks, ranging from 1.8 improvement over OCC for TBCC to over 3.9x on the tau bench workload. And we get better performance on this particular benchmark because this has a lot more longer transactions and more complex, in which if you choose the right schedules, it makes a much bigger difference. But overall, we see that we're able to perform quite well with our scheduling policy. So that's all nice, but as I mentioned, we do use a novel concurrency control protocol there, but it's not necessarily ideal for a lot of existing systems that already have concurrency control implementations. But actually, because scheduling and concurrency control are complementary techniques, you don't have to change your concurrency control. So we introduced a bolt-on scheduler, which we basically layer on top of the concurrency control that's only queuing the transactions at the start. Once they start running, we no longer control them. So to show the results of this, we have two concurrency control protocols locking OCC, which are the default ones in RocksDB. And we implement our scheduling policies bolt-on on top of them without modifying the existing concurrency control. So this makes it very easy to implement our scheduling policy without changing much of your existing system. And showing the results for these, so you can see that OCC and lock are the darker bars, and then our SMF is the lighter two in turquoise, and we get higher performance across all the benchmarks. Of course, it's not as high as with our novel concurrency control. So here it's like 3.3 instead of 3.9, because once those transactions start executing, we don't have as much control over the operations. But you still get most of the win with our scheduling policy. Finally, very quickly, I'll talk about results that we got on a production system. So as I mentioned, this was work in collaboration with Meta. So we ran a prototype of our scheduling policy on top of Tau, which is Meta's social graph data store. This stores all the data for the applications such as Instagram, WhatsApp, Facebook. And for the particular workload, we used Tau Bench, which is an open source social network workload that we open sourced about 2 years ago. That's actually representing the production workload that is running on Tau. And we compared against the Tau baseline on this Tau bench workload, and we saw significant increases in throughput as well as decreases in P99 latency, showing that it's feasible to run this policy on a very large production system. So in summary, we've shown that scheduling can have a pretty big impact on performance, and our policy is able to find these schedules very quickly, fast schedules very quickly, to see pretty significant wins on real-world workloads. So if this is something interesting to you in your system, I would definitely love to talk more. But I do have the second part of my talk. For the folks that just walked in this room, hi, I'm Audrey, fifth-year PhD, and this is 2 parts of the talk. So the first part of the talk was on transaction scheduling. We showed, we're able to get significant wins with our scheduling policy. But now that we have this problem of scheduling, there's this question of you're giving priority to certain people so they can have better overall performance. So what about starvation, fairness? What happens when you what happens to the people who have lower priority? How do you ensure fairness when you do have transaction scheduling? So this is follow-up work to the previous talk, and this will appear in SIGMOD next year. So again, this is work in collaboration with a bunch of folks, and it will be Batman themed. So I'm going to ask you to view a multi-tenant database as Gotham City. And this parallel works very well because Gotham City has a bunch of different residents, and similarly, modern databases have many applications that are increasingly sharing the same data, just as these residents in the city are sharing the same space. And as a result, there's a large variety of request patterns we're seeing as well, just as there's many different residents in Gotham, ranging from good doing citizens to many criminals. And that's why sometimes our databases end up, specifically our concurrency control protocol, ends up looking like this. You might have like a marketplace application trying to sell products. At the same time, the ad recommendation might be trying to run analytics on the same data. And these days, of course, can't avoid the LLMs and all the crazy processing they're doing on the data. So in these cases, we've seen that data contention has been a growing issue, and specifically the lack of performance isolation. So these tenants are affecting each other. Based on conversations and interviews we've had with engineers at Databricks, Meta, and Neo4j, we found that this is a growing problem. One example of this is like one tenant might suddenly see a burst of requests. Like let's say a celebrity posts a live video. Then a ton of viewers are trying to view this video. That could be affecting other applications that are also running on the same data. Another common pattern, a problematic sort of request pattern we've seen is one tenant might be sending very large transactions, like let's say some analytical application trying to do some pretty large transactions, also updating data at the same time that many other applications are doing shorter lookups, for example, and this can cause issues. So the standard status quo solution today is just put a gate in front of it, put some sort of request limit per tenant. So once you reach this limit, whatever it is, usually set by the system administrator, then we're going to throttle your requests. And this is very popular because it's very straightforward and simple, easy to understand. And for example, Tau uses this in many different ways. Actually, they're a little bit more aggressive. They say if one particular application is doing too much, we're actually going to put you in a lower priority queue to make sure you're not affecting everyone else. Obviously, this isn't ideal because it can lead to system underutilization. Like if you're the only client that happens to be accessing a particular key at a particular point in time, then you shouldn't be throttled. So in academia, the solution to achieve both performance isolation as well as high utilization is to use fair scheduling or fair sharing. Essentially here, each client gets their fair share. So if you have n resources, then each client should get 1/n of the resource, or they should get all those resources for 1/n of the time, depending on how you define your resource usage. And I'll go into more detail about this in a little bit. So specifically in this work, we're focusing on the problem of fairness for transactions. And we want to be mediating access to shared data items, also known as keys. So here, keys are the resources, and we assume here that contention is the bottleneck. So we care about logical contention. We're going to defer physical resource scheduling to other work, including, Tyler. Tyler's a student in my lab, and then we're going to enforce fairness on the per tenant and client level. So for fairness with multiple resources, there's been a lot of work on this, some of it from Berkeley. Dominant resource fairness is one very popular strategy. And here, essentially, what it's saying is you should equalize the dominant share or the maximum resource that each client is using, and that will give you performance isolation, as well as this property called strategy proofness, where you can't sort of game the system. I won't go into detail here, but you can. I added the papers here if you're interested in learning more. So this is all great, but why our database is still looking like this? And the key challenge here with transactions and ensuring fairness is transaction dependencies. Because prior fair schedulers sort of assume each job is independent and your resource usage is static, things are very simple. However, with transactions, they have dependencies both within and across requests. So the resource usage can vary, meaning that even your total system capacity can vary. And to see this, I'll give a very simple example. So specifically, we're going to be focusing on usage time as a resource. So basically, how long a transaction is preventing other transactions from accessing a particular key. And we assume that each operation takes 1 unit of time. So we build on the notion of virtual time, which was introduced in networking several decades ago. OK, so for the simple example, to see how resource usage is schedule dependent, let's say we have this transaction, T1. Robin is trying to update the list of criminals that he's pursuing. So he's reading and then writing to his own key. At the same time, there's another transaction, T2, that's reading to the Batman key and then reading and writing to the Robin key. So here, there is a conflict on that Robin key. So T2, since it waits for T1 for 2 time units, we say that its usage is 2. However, let's say the order of these transactions happens to be flipped. Then in this case, T2 takes 3 time units to run because there's implicit dependencies here between each of its operations, and then there's T1. So now, since T1 has to wait 3 time units for it to execute, the usage of T2 in this case is 3. So even though it's the same transaction, same workload, because of the order in which they execute, actually the usage can be different. So to address this issue, we introduced a new fairness policy called dominant resource fair transactions. That's basically leveraging the fact that you can actually calculate this resource usage after execution, and by doing so, we're able to retroactively go and update that usage based on what's scheduled after a particular request. So I don't have time to go into detail for now, but happy to answer questions, also talk offline. There's also an interesting trade-off in this particular setting between fairness and performance, because as I mentioned, since your resource usage is schedule dependent, there's two ends to the spectrum here. We might want to achieve fairness as fast as possible, equalize that usage across clients. But in many cases, if you're a little bit unfair, you can actually improve performance by a lot by delaying fairness, essentially, to reduce resource usage, which you actually saw in the previous part of my talk where I showed you, different schedules can give you vastly different performance. So now Batman has a moral decision to make. But actually how we deal with this is in the memoryless case, there's a very simple policy for this. It's just you choose the client with the lowest usage to go next. So to balance between those two goals, we introduce a delta parameter that's basically bounding how much the usage between clients can differ, so that you can introduce basically some delay in the system to get better overall system utilization. OK, so we also evaluate this protocol on RocksDB. And I'm just going to show a set of results on Smallbank, which is a standard OTP benchmark. And in this particular case, client 1 is sending twice the number of requests compared to client 2. So in the unmodified system, client 1, you see it gets about twice the amount of throughput to get under FIFO, like the default scheduling policy, to get around 4K transactions per second. On the other hand, with our protocol, we still get the same total throughput, but now we equalize the throughput of the two clients, which is fair in this case because they're sending the same workload. It's just one happens to be sending at a much higher frequency. So as I mentioned, this is work that will appear in Sigma next year. We're still finalizing the paper at this point. But if you've seen cases of like bursty workloads, maybe background tasks, or you've seen contention issues, or more generally, if you're interested in talking about transaction scheduling, definitely would love to connect after this. But in summary, for this work, we found that transaction dependencies introduce new challenges in ensuring fairness, and we've developed a policy that is able to account for this and ensure fairness while still maintaining high performance. So yeah, thank you. My email is there. I also have a website. And I mentioned TauBench, which I worked with Meta to open source about 2 years ago, is also running. We've collaborated with TiDB and PingCap to run that on their system as well. If you're interested in running it, please let me know. But yeah, thank you very much for your attention.